In this video, we will revisit some of the concepts of neural network which you should have already studied in your AI algorithms course. Suppose, let us imagine that you work for a bank and you are in the loan department and you need to build a model for predicting whether a customer has to be provided loan or not. For this, you are taking into considerations lots of features such as age, salary, the current bank balance, and the retirement status. So one way to build this classification model is to use a traditional machine learning approach like a logistic regression. In the logistic regression, we assume that the outcome will be the sum of these features or attributes. So your logistic regression will take into account the effect of these four features, but will not take into account the interaction between these features or how these features affect the overall loan process. This is where a neural network becomes important, because in a neural network we have hidden layers. And what are these hidden layers for? These hidden layers are to capture the interaction between these attributes. This figure shows the same problem but now designed using a neural network. So we have the input layer, the output layer, and any layers apart from this input and output layer is called as a hidden layer. In this example, we have one hidden layer which has 3 neurons. So while the input and the output layers corresponds to the apparent things that occurs or are present in the world and can be stored as data, but the values in the hidden layer are not something that relates to the real world or something for which we have data. So to repeat, the input and the output layers corresponds to something which is already present in our world and can be stored as data, whereas the hidden layers represent something other than this. So technically, each node in this hidden layer represents the aggregation of information from the input data. Hence, each node adds to model's capability to capture the interaction between the data. The more nodes in the hidden layer, the more interaction can be captured by these hidden layers. Or in short, a hidden layer is used to capture the interaction between your data present in the input layer, right? And it is actually the nodes of these hidden layers which calculates the aggregation between each of your input attribute. So this is actually one of the strengths for which you have your neural network designed. So back when we are just using a logistic regression model, the interaction between these four attributes are not captured when deciding the output. Whereas when it comes to designing the same problem using a neural network, we have the hidden layers and the nodes in these hidden layers which actually captures the aggregation between the input features. Let us now consider another example wherein which you are trying to help your friend who wants to buy a house. Your friend was quoted say $400,000 for a 2,000 square feet house. And the friend comes and asks you, is this a good price or not? Or is a $400,000 worth to be paid for a 2,000 square feet house in the particular neighborhood? Now, you decide to build a neural network to answer this question. But you cannot do this until you have a frame of reference. So you ask your friend to find out what is the prices of the nearby houses in that neighborhood along with the square feet of those houses. And your friend came up with this simple data set which has the area in square feet of each of the houses and the price in which the house was sold for in that particular neighborhood. And as you can see, there are 3 rows or what we call as 3 records in this data set with one attribute which is the area of the in square feet. And this is a labeled data set because we have the actual price which is Y. So the first instinct you would have is to get the average price per square feet. So based on these records, you find what is the average price per square feet of these houses. And when we compute this average, it comes to about $180 per square feet. And based on this knowledge, you come up with your very first simple neural network which basically looks like this. So this diagram shows you the structure of the neural network and how it calculates its output or the prediction. So as we can see, the calculation starts with the input node, and this input value flows to the right side where it gets multiplied by the average cost per square feet of this of what we have come up based on this data set, which is 180, and your input gets multiplied by this 180. And this 180 is nothing but the weight, or what we call as the parameter of your neural network. And the multiplication output technically becomes your prediction. So multiplying the 2000 square feet. So 2000 square feet is the house that your friend is willing to purchase. So multiplying that 2000 with this 180 will give us $360,000. So as we can see, this prediction of this output is just a simple multiplication operation. But what is more important is to come up with this value, which we call as the weight or your parameter. And in this particular example, we have just taken that weight to be the average cost per square feet based on the data set that was provided. So finding the weight in our training stage is what is that our neural network does. So whenever we say that we are training a neural network, it means that we are calculating or we are finding the weight or parameters for our neural network, which is used to calculate our prediction. So technically, I can write my prediction as y is equal to w into x, where y is my predicted value of the price, which is equal to my weight w into x. So that is nothing but y is equal to 180 into x. Now for simplicity, let us switch our price unit from $1 to $1,000. So I can just rewrite this y as y is equal to 0.180x. So let us see the same example with the help of a simple animation. So the blue dots are nothing but to the 3 data points you have collected, and the line shows the model that you have built, which is based on y is equal to 1.180 into x, and based on that, for a 2000 square feet house, we get the price to be $360,000. Now, moving on, we have to try to answer the question, can the neural network that we have built, can it perform better, or can our neural network give us a better estimate of the price based on the data points, or based on the average of our data points? For this, what we will do is, of course, we have our area. We have the actual price for which that house with the particular square feet of area was sold. Of course, we have converted the price from $1 to $1,000. That is why it appears as 399.9, right? So this is the actual value of Y. Now, based on the model that we have built, which is Y is equal to 0.180x, which was based on the average price per square feet based on our data set, what we will do is we come up with the predicted value of Y. So based on our model we have created, the house with square feet 2104 was sold for a price 379. So this, what we see in red, is the predicted value of Y. Now we create another column which is the difference between the actual value of Y, which is this, minus the predicted value of Y. And based on that, we get these values in yellow. Now, as you can see, there are some positive values and some negative values. So what we do is just find the square of those values. And this column is now what is referred to as our mean squared error, or also known as loss function or cost function. So we will now use this mean squared error or the loss function or the cost function as a guide to train our neural network. So going back to our question, can our neural network do better? The answer is yes. Our model can do better. That is, we have to come up with a better model, that is the one that has got less mean squared error. So I have, based on the model I have created, my average error is 2058. So what I want is to come up with a better model. It means that I have to decrease this error, or I have to optimize my cost function. Now again, this is just a visual representation of what we have done. So this is our visual representation of what we have just discussed. And what you see, this yellow line is actually the value of, or the difference between the predicted value of Y and the actual value of Y. So what we see in that yellow line is what we wanted to decrease, right? So I want to decrease the length of that yellow line for each of my data point, so that at the end my average error will be decreased. So in order to come up with a better model, of course what we have to do is to experiment with our weights or the parameters of my neural network. Remember, the first neural network we have built was based on y is equal to 0.180x, where 0.180 was my parameter or the weight. So now what I have done is I have taken a different value of my parameter, which is 0.190, and I have done the same process from my slide before, which was to come up with the actual value, which is to come up with the predicted value of y, and then to find the difference between the actual value of y and the predicted value of y, and squaring it and then taking its average to form our mean squared error. So as you can see, when I do it for this particular model in which I have the weight as 0.190, I get my error to be 2746, which is actually worse than my previous model which I have built, which only had 2058. So I test another value. I decreased my value and then I made a model as y is equal to 0.160x, and again I found the mean squared error and I got it to be 3229, but again it is greater than 2058, which means this model is also performing worse than the first model I have built, which was based on the parameter 0.180. So based on these two experiments with the weight, it is very clear that just by changing the slope of our line, right, we cannot seem to come up with a better model. So what we do now is change my formula from y is equal to just wx to y is equal to wx plus b, where this b is called as a bias or the offset, and it is also a parameter like w, which my neural network will learn during the training phase. So this equation is now resonating with the equation of a straight line, where we say the equation of a straight line is nothing but y is equal to mx plus b, where m is the slope and b is what is called as the y-intercept. So now my diagram of the neural network looks something like this. So I have my input x, which is multiplied by w, then added with bias to give my output y. And now having this equation y is equal to wx plus b, I further experiment with the values of w and b, and I came up with this model where w is equal to 0.100 and b to be 150. And based on that, I computed the predicted value of y computed the difference between the actual value of y and the predicted value of y, squared those values, and found its average to come up with my mean squared error. And as you can see, I get the mean squared error to be 799, which is far less than the actual error I had for my first model, which was 2058. So now I can conclude that my best model is y is equal to 0.1 x plus 150, where 0.1 is the weight and my b is 150. Now this finding of weight and bias, or my parameters of a neural network, I just did it manually, trying with different values of W and B. Whereas when you start to build your neural network, we do this process with the help of the optimization algorithms like gradient descent. So we use algorithms like gradient descent to minimize our cost function, or the loss function, or the mean squared error. And the derivative of this loss function will tell us in which direction we want to change our W and B in order to minimize this error. So, during the training of my neural network, I have a forward propagation which calculates my y value, and then I have a backward propagation wherein which I will be trying to optimize my error by altering this W and B. Now suppose, other than the area of the house in square feet, you were also able to track the number of bedrooms for each of these houses along with the prices. So in this case, we have two attributes of features: area of the house in square feet, and the second attribute, which is bedroom. And based on these two features, I need to calculate the value of y, which is the price of the house. In that case, my new neural network will have the formula y is equal to w1x1 plus w2x2 plus b, where of course x1 and x2 are the two attributes, and w1, w2 are the parameters or the weight, and b is the bias. In that case, the neural network will be now something like this.